Bangalore, where he worked on the development and implementation of algorithms for LTE and IEEE 822.11 AC wireless standards. In 2021, he was a postdoctoral researcher with the Department of Electrical Engineering, Linköping University, Sweden. His research interests include wireless communications, multiple antenna techniques, spectrum sharing, and next-gen wireless standards. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Over to you, Professor.
Okay, firstly, thank you for the invitation and kind introduction. Just give me a confirmation that you're able to hear me, right?
Yes, sir.
Okay. Yeah, I'll be talking about this intelligent reflecting surfaces, which has become very hot topic right now, and like mainly focusing on trying to combine it with the traditional antenna selection with the main focus on reducing the complexity. So this will be the broad outline of my talk. First, before I go into the actual theoretical part or our contributions, I'll briefly show the field trials and the prototypes that are being developed for intelligent reflecting surfaces across the world. Then we'll shift to antenna selection, and then I'll focus on our system model and channel model, for which I'll try to develop the optimal selection algorithms, and I'll conclude with a brief summary. To start with, intelligent reflecting surfaces is being envisioned as a key technology for the next generation wireless communications, which is basically the surface is a two-dimensional planar thing as shown in the animation on the top. Each element is made up of an artificial electromagnetic metamaterial surface, which can be electronically tuned to.
Hi, Nilesh here. I don't see the slides moving forward. I see only the title slide.
Oh, okay. Is the same with everybody else? Like,
yeah,
Yes.
I think you're still on the
Yes.
first slide, Sarvendranath.
Yes, same thing here.
okay. I'm not sure what happened. So, okay, now like I came out of the full screen. Do you still see the first slide?
No, now we see the new slide, but it's not a full screen now.
Yeah, I think, okay, I'll just go to full screen now. So which slide do you see now?
Intelligent reflecting surface.
Okay, okay, that is the current slide. Okay, I'll try to switch the slides. Just let me know. Are you able to see the change in the slides?
Yes, now.
Yes.
Okay, just I'll go back. Okay, let me continue. So as we are discussing, like this, each element of this reflecting surface can be electronically configured so that like the entire surface can beamform or focus the signal in a desired direction, which can help in the situations where we cannot have a direct signal reaching the users with a significant strength. So we are calling this kind of beamforming or focusing the signal in a particular direction as passive beamforming, as it is mainly achieved without the requirement of active radio frequency change, which are in general costly and power consuming, and which generally has like a lot of components as shown in the picture below here. And the gain we get through this passive beamforming is shown theoretically at least to be proportional to the square of the number of IRS elements, which we are we are getting this gain in a very cost and energy efficient manner. There was a lot of interest towards development and theoretical studies of this particular field. From last 2-3 years, it has gained a lot of interest. So before going into the theoretical work or my work, like I would like to show some of the prototypes that are being developed across the world. Okay, I'm not an expert in this metamaterial surface or anything, but I'll just show you what is happening. Like recently there was a prototype in China where they have developed 1100 reflective element reflecting surface controlled by varactor diodes, specifically for 5.8 gigahertz band, and like which was shown to have a power consumption as low as like 1 watt, like compared to the base station kind of powers. And they have also verified the channel reciprocity assumption being valid for IRS. And they have shown that like in indoor scenarios, they were able to achieve a 26 dB power gain. And in the outdoor short range scenarios, like roughly around 27 dB gain. So we'll not go into these details, just to show thing that it's being practically implemented, and like there are good number of practical test beds. So this is the picture of the test bed they have implemented, where transmitter and receiver are controlled using an USRP and using the 1100 element IRS, which we have seen in the last slide. So basically the plot on the right actually shows the amplitude and phase of the configured reflection coefficients as a function of the frequency when different amounts of voltages are given to the varactor diodes. Basically, it's of interest for us is like the thick band shown at the center, like that is what is 5.8 gigahertz where this test bed is operating. If we see the plot below, you can clearly see by varying the voltage given to each of the IRS element, we can change the amount of phase shift it has introduced to the reflected signal. So this way, like we can configure the tunable parameters of the IRS. So this is just to give an idea like how the actual IRS are being designed. So I'll just show one slide on field trials. So the same prototype which we have seen till now has been deployed once for in short range outdoor scenario, where the transmitter and IRS are like roughly 50 meters apart, and they were able to show a gain of 27 dB with IRS, where like you have a significant amount of signal present, and like without IRS, like we have like a very small amount of signal compared to the noise. And they have also done a similar experiment in a long range scenario, where I mean like transmitter and IRS are at like 500 meters apart. They were able to show a gain of like 14 dB with the help of IRS. So these are like the practical gains that are being demonstrated with this emerging topic. So like there are many other prototypes using different technologies that are being developed. Like this is one of the prototype where they tried to build an IRS with 100 cross 100 reflector elements in an roughly around 1 meter by 1 meter size, where each element is having a dimension in each direction roughly 0.35 times the lambda, where here the lambda corresponds to this 10.5 gigahertz. So basically the frequency of operation is very important in this IRS design. And also, as we see, there are like other prototypes like 8 cross 32 units, where each element is having roughly 0.17 lambda and designed for 4.25 gigahertz. So there are multiple other prototypes, like where they are using some other technology. Like this is one prototype where they were using pin diodes to basically get the configurability in terms of phase shifts introduced. So basically there are different 5 number of pin diodes here, and by getting 4 different on-off configurations, they're able to introduce 4 different phase shifts to the incident signal, and demonstrated around like 27 dB gain at 2.3 gigahertz. And the last prototype before we move on to antenna selection, this is another prototype which they are calling it as scatter MIMO, mostly demonstrated in indoor scenarios, especially in 5 gigahertz Wi-Fi band using 11 AC standard. So basically this reflecting surface is built using 48 patch antenna elements, like each like 3 tiles here, and each tile having 16 elements, and they were able to show an indoor coverage extension by 15 meters, like with as low power consumption as like roughly around 14 milliwatts. So these are like the some practical numbers we are seeing in terms of reflecting surfaces. With this, I'll move on to the actual topic. So this is all just to give you a glimpse like on the practical side. So as I initially told, we'll be discussing about intelligent combination of intelligent reflecting surfaces with antenna selection today. So we have seen like in the initial slide, like intelligent reflecting surfaces are using some passive reflective elements in the place of active radio frequency chains, whereas antenna selection also has a similar objective, like it try to reduce the cost and the power consumption. But here, instead of replacing, it tries to reduce the number of radio frequency chains at the transmitter. For example, the picture here shows a transmitter with multiple antennas, however, with only one radio frequency chain that is being dynamically switched to one of the antennas. So when we try to select antenna based on the channel conditions, and we select when we select the antenna with the highest or the maximum gives the maximum benefit, it is shown to achieve full diversity, by which I mean the diversity which we would have obtained by having number of antennas equal to the number of RF chains, or like the RF chains equal to the number of antennas. Due to these multiple antenna benefits with low hardware cost, antenna selection is also part of several wireless standards. So this is about the brief idea about antenna selection. So moving on to our actual system model, which is having this objective to combine the benefits of antenna selection and intelligent reflecting surface, both in terms of cost and energy efficiency. So the picture here shows our system model, where transmitter has NT number of antennas and NRF number of radio frequency chains, which are smaller in number compared to the number of antennas. So this transmitter is trying to communicate to a single antenna receiver with the help of a reflecting surface having N passive elements, which are controlled by a controller. So this is our system model. And next, I'll briefly talk about the channel model, how we are considering. So basically, we have two types of links in this system with aided by intelligent reflecting surface, or IRS. So basically, one is a direct link that is directly received from at the receiver from the transmitter, that is TX to RX direct link, which we are modeling it as a relay fading channel in the typical scenarios from base station to user, where there are no significant line of sight component from transmitter to the receiver. And whereas in the reflected links, that is whether transmitter to IRS and IRS to receiver, we consider a Rayson fading model having both line of sight components and non-line of sight components. Um, Considering a scenario where IRS is placed in such a way that it is able to see a line of sight both from the transmitter to the receiver. Maybe you can visualize it from the picture we have seen initially when we described IRS, where reflecting surface is able to see a line of sight component from both from the base station and to the users. So to model such a scenario, we consider these reflected links as Rayson fading. And like other typical assumptions, like we consider time division duplexing to avoid the feedback and to exploit reciprocity, and block fading model where channel remains constant in coherence interval. And in terms of channel assumptions, we only assume that transmitter knows the channel gains, and IRS doesn't know any of the channel gains, because some of the literature also assumes IRS knowing the channel gains, but it's typically difficult for a completely passive reflecting surface to be able to perform channel estimations. So we don't assume any channel information at the IRS in our model. So for this system model and with the channel model I described in the previous slide, our main goal is to jointly optimize the subset of antennas at the transmitter and corresponding transmit beamforming vector for the selected antennas, and passive beamforming at the IRS, by which I mean configuring the reflection coefficients at the IRS. So all these three variables need to be jointly optimized such that I receive maximum power at the receiver. So that is like my goal of trying to optimize three variables. So for this goal, like our contributions are like twofold. So firstly, single antenna selection, by which I mean I select only one antenna in a scenarios when the transmitter is equipped with only one radio frequency chain. I would only select one antenna. For that, we have derived one simple optimal selection rule. But to reduce further complexity, we have also proposed a simpler selection rule. I'll discuss both of them for a single antenna selection rule. Moving on to subset antenna selection, where I would select more than one antenna at the transmitter. This applies to scenarios where I have more than one RF chain and I select a subset of antennas. Here I have developed one manifold optimization based optimal algorithm for selecting all the three variables jointly optimal. And again, to reduce complexity, we have developed an simpler alternating optimization based algorithm. So I'll start with the single antenna selection first, where the number of radio frequency chains NRF is equal to 1. So let the antenna selected be denoted by letter S, and the IRS reflection coefficient of nth element be denoted by Xn, which is nothing but I have taken it to be simple, like e power j theta n, having an unit magnitude. So in this simple setup, all the channels becomes mostly scalars, and the channel complex channel gain from transmitter the selected antenna of the transmitter to the receiver be denoted by HDS, D denoting the direct link, and the channel gain from transmitter to IRS as GNS, corresponding to nth element and S antenna. And for the reflected channel gain from IRS, nth element of IRS to receiver as HRN. When the transmitter transmits a symbol D using a maximum power Pmax, so receiver receives the signal through two paths, one direct path, that is the first part, and the second part in the received signal shows the combination of all the signals reflected from all the n IRS elements. So this Y being the received signal for the antenna selected and the reflection coefficient Xn. The problem statement here is slightly simpler, where we only have to optimize the antenna index and the corresponding reflection coefficients at the IRS to maximize the received signal power. So this is the objective. So basically, this is a simpler problem, and I would not go into the derivation. It's a simple, straightforward one that is available in conference paper we published. So I would instead like give you the final result and try to explain the intuition or insights we can gain from the final result. So the slide here shows the structure of both optimal antenna index and the optimal reflection coefficient. So SOP, the optimal antenna index, is the one that maximizes the metric shown here. For each antenna, for suppose a kth antenna, we see the metric that is being computed and compared against is nothing but the sum of absolute values of direct link channel gain, that is HD, and the product of both the channel gains from transmitter to IRS and IRS to the receiver. So which I would refer as cascaded channel gain from here onwards in the talk. So we see the optimal antenna is the one that maximizes a metric, which is nothing but sum of direct link channel absolute value and the cascaded channel gains absolute values. Once optimal antenna SOPT is selected, sorry. So is somebody trying to write something? Okay. Okay. So moving on to the once the optimal antenna SOPT is selected, to compute optimal reflection coefficient, all we have to do is compute the phase, the difference between the direct path channel gain and the cascaded channel gains through the nth element of IRS. That would give the optimal reflection coefficients phase for nth element again. We have to repeat this for each and every IRS element. So interesting thing to note here is optimal antenna depends only on the absolute values, and it doesn't need any phase information. And whereas optimal reflection coefficient depends only on the phase information, and it doesn't need any absolute or information about the absolute values. And okay, this is over. And we also see one interesting thing is like decoupled nature. I can compute the SOPT without needing to compute the optimal reflection coefficients. I can directly compute them because it only depends on the absolute values. So these are the two interesting observations from simpler closed form optimal rule. Yeah, it's like very simple. Like we have closed form for both SOPT and XNOPT, so we can easily implement. So what is the problem here? Like, is there any challenge to implement this? Just let me explain the main challenge in implementing this simpler closed form optimal rule. So the main challenge here to implement would be the number of pilot transmissions required to obtain the channel state information required to implement this rule. So to understand that, let us just focus on the optimal antenna index and the selection metric of one antenna. Suppose I want to compute the selection metric of one antenna, suppose like kth antenna. So I need one direct link channel gains absolute value. For that, receiver need to transmit one pilot, and the transmitter need to estimate the channel when the IRS is in off state. And for computing the second part of the metric, I need to turn on each and every element of IRS one at a time, and receiver need to transmit one pilot, and the transmitter need to estimate one cascaded channel gain. So if we see, so totally we will need total capital N plus one pilots for each antenna to estimate the channel gains and compute its corresponding selection metric. But because we only have one radio frequency chain at the transmitter need to shift to each and every antenna and receive pilots from the receiver. So total receiver will need to transmit something like NT times N number of pilots, which will typically be huge in number, as the number of IRS elements are generally large, as we have seen in actual practical prototypes also. They are of the order of 1,000 and higher. So the amount of pilots required to transmit and the amount of time taken to obtain this channel state information increases and poses a challenge to implement this in practice. So to reduce this pilot transmission overhead, we try to develop a much simpler selection rule, which we obtained by just modifying the selection metric of optimal rule little bit. So we just instead of trying to get the sum of absolute quantities, we replaced that part with the absolute of sum. By triangle inequality, we definitely know that the selection metric of lower complexity or last rule lower bounds the selection metric of optimal rule. But let us try to understand how does this really help or reduce the number of pilot transmissions. So in order to understand that, like, let me explain a scenario. Suppose if I configure all the IRS elements with the reflection coefficient as 1, and receiver sends one pilot, whatever the signal received at the transmitter can be written as this at the kth antenna. So if we closely observe, when we configure IRS in such a way and receive a pilot at the transmitter, so whatever the sum of the cascaded channel gains, whose absolute value is needed by the lower complexity rule, is directly available in the signal received. So by receiving one pilot, I can get this quantity and estimate the absolute. So to obtain the metric of this lower complexity selection rule, especially for the second part, I just need to transmit one pilot from the receiver compared to capital N number of pilots required by the optimal rule. So which we have seen in detail in the last slide. So because of this, the total number of pilots, which are of the order of NT times N for optimal rule, reduces to just NT, which is typically a smaller number as a number of antennas at any of the base station. So we see a significant reduction in the number of pilot transmission required to implement this lower complexity selection rule. So let us also try to look at how the performance of this system would be by having such lower number of pilots. So to understand that performance comparison, I have just shown average symbol error probability as a function of peak transmit power, Pmax, in dBm. We see the performance of the optimal rule, that is in blue solid line, is very close to the performance of the low complexity rule, that is shown in red dashed line, where both the all the curves here of optimal and last rule correspond to having 4 antennas, and out of which one antenna we are selecting. We clearly see that performs better than an antenna with single RF chain and single antenna, that is shown in black solid line. And so this shows that last rule is near optimal in terms of performance. And also we see as increasing the number of IRS elements, we definitely improve the performance significantly. So this is about single antenna, optimal rule, simpler rule, and its performance. Now I'll move on to subset antenna selection, and I'll
Hi, Nilesh here. Just a question.
sir.
The previous slide, what sort of antenna, what sort of element spacing do you have in your simulation setup?
Lambda by 2. All these are simulations are for 2.4 gigahertz, and all the element spacings are lambda by 2. And yeah, like these simulations are done with independent channel modeling only. Like we haven't considered the correlated channel modeling as it's being considered in recent IRS literature.
Right. So then it's a little mysterious that it's so close to optimal, because you're essentially having them add up in all sorts of phases, and somehow it's still able to select the best antenna. Any
Yeah,
idea
so
why
that's
it is
mainly
working?
one thing is, like, due to lack of time, I did not go into detail. So because I only showed the how I'm modifying the antenna being selected. So once this antenna is selected, I should have explained, like I didn't go into detail. So what I was doing is, once the antenna is selected, I am still trying to configure the phases in this way, which is general optimal for that particular antenna. So that's what is actually helping, because once for any antenna selected, I try to still compute the phases which would be the optimal phases for that particular antenna. So only the problem here is the difference from the optimal to this low complexity would be the antenna selected. Even if the optimal selects the same antenna, it would have configured the same phases. So what I observed in my simulations is, like, okay, the antenna is not like really the one which is degrading the performance much, but if I don't configure the phases in this way, performance really is bad.
Thanks. Yeah, last question. So to get the phases, wouldn't you again need a order n training?
Yes. Order n would be needed after the antenna is selected, but that training I'll do only for the antenna selected.
Got it. Okay, thanks. Yeah.
So that will be like only n times 1. It won't be like nt times n.
Yeah, thanks.
Yeah, so I didn't show you the actual values. So the actual thing would be needed here would be like for last rule, it would be like nt plus n, but only for selecting the antenna it is n, but for computing the phases it would be like nt plus n compared to like nt times n required by optimal rule. That is still significantly low.
So one other question, if I may.
Yes.
Is there any assumption of channel symmetry gains being symmetric in the two directions, from transmitter to receiver and the other way?
Yes, like I have considered time division duplexing, TDD, and under channel reciprocity.
Okay. But is channel reciprocity something which is seen in practice, or it's a
Yes, like as I mentioned in the initial slides, it's been shown practically in this particular work. Like they verified the
okay?
IRS channels being reciprocal.
Okay, okay, fine. Okay, thank you.
Yeah, so let's move on with the subset antenna selection, where the number of radio frequency chains is greater than one, and I would select subset of antennas now. So in addition to the antenna indices and passive beamforming reflection coefficient X, now I also have to optimize the transmit beamforming vector W. So without going into the mathematical details here, the signal power which I'm trying to maximize would take this particular form, which is function of all three variables: subset S, the passive beamforming vector X, and the transmit beamforming vector W. So I want to maximize this subject to the transmit power constraint, norm W square less than P max, and I want to impose get the maximum reflection and impose a unit modulus constraint on each of the IRS element. So this problem is mainly complicated to solve in general because of the non-convex nature of this unit modulus constraint. However, like all these capital N number of constraints in total together form a nice structure called manifold. Like I'll briefly talk about those, though I'm not an expert in those. Like I just understood their basic idea and used in this developing this algorithm. Manifold is something like a topological space that locally resembles an Euclidean space. So the whatever the optimization techniques or the algorithms developed for Euclidean spaces can be adapted to this manifolds, and like we can obtain the equivalent optimization algorithms. So I'll leave it at that point. And the unit modulus constraint, where like each of the constraint is a like complex circle with your unit circle, and when we combine all of them forms like the product of n complex circles as the constraint, forms a nice structure called complex circle manifold. So because of this structure, we can use some optimization techniques like any of the standards like conjugate gradient equivalents for manifolds to implement or solve the optimization under this kind of complex circle manifold kind of constraints. So to do that, like what we do is like given a subset, suppose like I fix the subset of antennas, and for a given reflection coefficient vector X, I can easily write the corresponding transmission beamforming vector, the optimal beamforming vector, which is nothing but maximal ratio transmission vector. So once I know a given S and a given X, this is the optimal, I would substitute it back into the signal power, which we have seen in the last slide, to simplify the optimization problem to this, where the optimization variable is only X, which is the reflection coefficient vector, because I have fixed the S and like I substituted this W here. So solving this optimization problem is doable by using these manifold optimization techniques. So using this, we have developed this manifold optimization based algorithm, which basically loops over all possible subsets and tries to, for a given subset S, tries to solve the optimization problem shown at the bottom of the slide, and at the end of the loop it tries to see which subset gives me the maximum possible signal power, and takes the corresponding reflection coefficient vector obtained by solving this PS as the optimal reflection coefficient vector. Once the optimal subset and xopt is given, again we can compute the optimal W using the closed form expression given here. That is nothing but MRT transmission. So we have the combination of all three variables, sopt, wopt, and xopt as the return of this manifold optimization algorithm. But however, the problem here is like the problem we have observed with single antenna selection is like, though the optimal rule is in nice closed form, the number of pilot transmissions required to implement that algorithm was huge. So we targeted reducing that. But here, in addition to the pilot transmissions, even the computational complexity is involved. I'll briefly discuss that in the next slide. So if we try to analyze this algorithm and see the optimal complexity of each one. So first of all, it tries to loop over all possible subsets for a given NT number of antennas and NRF number of RF chains. The number of subsets will grow as the order of NT power NRF. So it increases exponentially with number of radio frequency chains. And even taking an example of conjugate gradient equivalent algorithm for manifolds, solving each of this problem for each subset, it takes a complexity of the order of n power 1.5. As it is a function of the number of IRS elements, the total complexity is huge, as the number of IRS elements is typically large. As we have seen, it can be of the order of thousands. So the main challenge here for a subset antenna selection, in addition to the pilots, would be the computational complexity. So again, we try to tackle this computational complexity and lower its the complexity. So we developed another algorithm using the alternating optimization technique. So here we have used a lot of insights developed while developing the single antenna selection rule. So firstly, to reduce the number of pilot transmissions required, what we did is we computed the selection metric of loss rule for each of the antenna. For all the NT antennas, I compute the metric of loss rule, which requires significantly lower pilots than the single antenna optimal rule. Once I compute these selection metrics, I simply sort the antennas based on the selection metric. And first, I select antennas with the highest selection metrics, or like the first NRF antennas I select and put it in my selected subset. So step one finished the selection of subset. So for now, for this given subset of antennas selected using the selection metric of loss rule, I iteratively optimize X and W in an alternate manner. So first I'll fix W, which I can randomly initialize or initialize using the maximal ratio transmission only towards the direct link. And then given that subset is fixed and W is fixed, now the optimal X can be easily extended from the single antenna selection rules optimal reflection coefficient, which we have discussed earlier. So now for this updated X, for the same subset, I can update the W by substituting that X in this MRT kind of closed form expression available for W. So now I'll repeat this procedure of optimizing W and X till I see a convergence in the signal power. So this way, this is a simpler alternating optimization based algorithm which uses very simple closed form expressions to compute reflection coefficients and the transmit beamforming vector in each and every step. So we see, if we try to compare the computational complexity and pilot transmissions of both manifold technique and alternating, we see a significant reduction. As we see, manifold one has an exponentially increasing in terms of number of RF chains, and it also is n power 1.5 in terms of number of IRS elements, whereas the alternating technique is only linear in terms of number of IRS elements and has additional complexity of NT log NT, which is typically smaller because the number of antenna elements is smaller. And also in terms of pilot transmissions, yeah, these are the number of pilot transmissions required for including both transmission for first and second phase. Like I haven't shown this complete structure for single antenna one. So, but still we'll have a significant reduction from NT times N to just N plus NT, which gives us a significant advantage in terms of pilot transmissions. So, but however, we are, or whatever the antennas selected and whatever the transmit beamforming vector computed, we are still trying to compute the optimal phase that will ensure the coherent combination at the receiver. So we still get a very good performance, which I'll demonstrate using just one plot. So again, to compare the performance of this manifold optimization algorithm and alternating optimization algorithm, I have shown one plot with similar probability as a function of Pmax. Here, the manifold optimization, which is supposed to give the optimal solution, is shown in the red dashed line, and the alternating optimization one is shown in the blue solid line. We again see they are like very close, though we see a significant or like small amount of gap between both of them. But for the amount of complexity reduction and the amount of pilot transmissions we are reducing, I think we can go with the alternating optimization technique. And we have also compared it with semi-definite relaxation method proposed in the literature, which is generally developed for a system with a number of RF chains equal to the number of antennas. So the performance of SDR or semi-definite relaxation is shown in the black solid line here. As we see, with for the same number of radio frequency chains, that is 2, as we increase the number of antennas from 2 to 4 to 8, we clearly see an improvement in the performance with the same number of RF chains. So implementing these selection algorithms has definitely improved the performance for the same amount of hardware cost in terms of RF chains. So this would kind of conclude both single antenna selection and subset antenna selection, which I wanted to discuss. So I'll now try to summarize what we have what I tried to convey in this talk. So basically, I was trying to allude that like combining the intelligent reflecting surfaces with antenna selection improved the performance while getting the benefits in terms of both in terms of cost and in terms of power consumption. So for to demonstrate this joint benefits of both, are developed optimal selection algorithms for both single antenna scenario and also for a subset antenna selection. For a single antenna selection, I was able to show that we have a nice closed form structure. And also we have seen it to be decoupled in terms of optimal antenna index and optimal phase coefficients or reflection coefficients are decoupled. But however, in the subset antenna selection, we were not having such a nice optimal closed form rule where we had to go for manifold kind of involved optimization algorithms. So to reduce both pilot transmissions and the computational complexity, we try to develop low complexity rules both for single and subset. In both the scenarios, we have reduced the pilot transmissions and the computationals or the number of computations required significantly, and using the numerical results, we saw that both low complexity rules are near optimal. So with this, I would conclude my talk and can take any questions.
So one quick question. In this, the subset antenna selection problem, if you look at the optimal policy, can you show that what is the complexity again? I'm just trying to understand that expression. Yeah, what is the, how did you get this NT to the NRF? Just can you?
Yeah, that's like, so like if I'm trying to loop over all possible subsets. So I have like NT number of antennas and I want to select NRF out of them. So I have NT choose NRF, those many number of possible subsets. So it's just a combinatorial number of combinations possible. NT choose NRF has a typical complex.
So then I messed up something. What is NRF? Was it the, what is NRF?
Is the number of radio frequency chains available at the transmitter, or you can see it as number of antennas I'm trying to select out of NT.
Okay. Number of antennas.
So I have NT number of antennas. I'm trying to select a subset out of them equal to NRF.
Okay. That's... Okay. What was the N? Was the number of reflecting elements?
Yes, capital N is the number of reflecting elements at the IRS.
Okay. Okay, so the order is NT to the NRF.
Yeah, that's like the number of subsets. And for solving for each subset takes a complexity of n power 1.5, specifically for conjugate gradient equivalent algorithm for manifold. So because I have to solve this each problem PS for nt power nr of times, so it's just product of those two.
Okay.
So basically the complexity of each iteration is n power 1.5, and I have to loop over number of times that is order of nt power nrf.
Okay, all right. Thanks.
So I have one question. So you mentioned this alternating optimization, right? So and does it converge all the time, or there are any issues in the convergence?
Okay, I haven't as such done the convergence analysis in terms of theoretical, but like yeah, numerically definitely it was converging, and it was converging pretty fast. Like in 4 or 5 iterations, it was like converging to a signal power, what it is like. So it is definitely converging, but I haven't done the theoretical analysis.
Okay, because I think it is similar to the alternating projection method, right, in optimization that you use. When you have multiple variables, you keep one fixed and then you optimize over the other, and then do the same thing with the other variables. So there might be some instances where it might not convert. So there are some, I think, conditions that needs to be satisfied for the convergence. So maybe you can look at that.
Yeah, that's a good point. Actually, I didn't try to analyze the conditions for convergence. Actually, that's a good point. Actually.
Yeah, and one more point. So basically, the goal of selecting the coefficients is intuitively to just have a constructive type of interference at the receiver. Is that intuitively what the goal is, or
yes,
is it something different?
Yeah, so basically you're receiving signal from both direct link and reflected links, one through direct link and capital N number of through the reflected link. So you want all n plus 1 to add up coherently or constructively to maximize the signal received. Yes, that is correct actually.
Okay, thanks.
So, Sarvendranath, Nilesh here. Any thoughts on how this would change if you had lambda by 8 spacing in the RIS elements? Like, so essentially lots of correlation.
Yes, sir. Like I have done the simulations, like as part of a journal extension I have done. Like they are not part of this conference, so I did not include in here. So what we have seen is like not much difference in terms of rate. Actually, it is helping in terms of rate, but when it comes to the metrics like outage probability or the symbol error probability, it is degrading compared to lambda by 2. Like which I have shown, the plots I have shown are for lambda by 2, but if I show a plot of symbol error probability with lambda by 8 spacing, it is much worse. Like so definitely and especially with correlation modeled, it is much worse. Both outage and symbol error probability kind of degrade, like the way diversity order goes down. But in terms of ergodic rate, it was not impacting much, but it is definitely it is not negative. It was like improving actually. There was one research article also which showed that correlation among antennas is bad, but like correlation among IRS elements is good in terms of rate.
Yeah, I agree. Yeah, makes sense. Yeah, thanks.
I have one question. So in the single antenna selection case, there are two schemes, right? One is the optimal and other is the last that you have proposed. So the metrics are a bit different in the sense you're bounding this particular first, the second term. So now this says that if you take, let's say NT grows to infinity, then you're taking max over so many variables. So my question is, if in the asymptotic regime of NT, will the statistics of both the optimal rule and last be the same?
Okay, that's a good question. Like,
If not, I was
haven't-
just thinking that gap between the blue and the red curve that you showed might keep increasing with NT.
Yeah, so it's like I haven't seen. Okay, maybe in the asymptotic sense, but I don't see actually. The thing was like mostly the plot I have shown is for mostly for simple error probability, who's like actually the slope or whatever is being mostly guided by the number of IRS elements, as the diversity order is like the number of IRS elements plus NT. Like, so I won't think like there will be a gap between the performance of both the rules as NT increases, as long as we choose the phases to be optimal once the antenna is selected.
Okay. Okay.
Because even the performance of a single antenna with a large number of IRS elements, it all depends. I don't think like the gap should increase with number of antennas, as long as we program the phases optimally after selecting. Yeah, maybe like for large number of anti, maybe I should take a careful look at it. Like, I don't have an answer right away.
Yeah. And this study is for a single user, is it right?
Yes. Whatever. Like, I was actually trying to just present the work in this WCNC conference paper. Yeah, we have extended it for multiple users, and that paper is still under review. Like,
okay. Yeah. Thanks.
yeah, it's for multiple users, like the objectives and all will change. Like, either you have to go for some data rate or something like that, and you won't get such a nice closed form expression. But like we can do some. We had to resort to some kind of optimization algorithms only in the case of multiple users.
Yeah. Thank you.
Thank you, Professor Sarvendranath. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. Thank you and have a great evening.